Hello, I'm John Furrier here at theCUBE in Palo Alto, California for a deep dive kind of news analysis on the big Broadcom launch of Tomahawk 6, an AI moment in networking, a big deal, Ethernet as it continues to thunder away and scale and deliver the value, scale up and scale out is the big story. Pete Vecchio's here, data center switching product line manager at Broadcom. He's got the keys to the kingdom on all the new switching products, breakthrough performance, scalability, open ecosystem. Pete, great design. Congratulations, you got props here. We'll go through that, but thanks for coming on.
Yeah, great. And thanks for having me.
We saw you supercomputing, obviously Tomahawk 5. We saw the breakthrough there. And again, great product at the right time. AI ushered in with the large clusters, the GPU surge. Now people are like, they're seeing it. They got visibility into the value. Now they're like, okay, I got to expand my operations, but they got constraints. They got power, there's efficiency, and there's a premium on performance, not just raw performance, but like performance within the system. There's like a system within the system. This is kind of like the inside the ropes, but this is a really big concern when you're designing large scale out and now scale up systems. You're not talking about how my GPU performs, we're talking about how it all works. This is kind of where the magic is with Tomahawk 6. Let's get into it. First, let's set the table. What is the big driver of the launch? Was it demand, just right in the cadence? Give us a quick overview of Tomahawk 6.
I think the big driver is the bandwidth demands. I mean, what we're seeing both for scale up and scale out networks, the bandwidth demands are insatiable. I mean, we can provide an infinite amount of bandwidth and it would be taken immediately. Along with that, however, you do need to have good congestion control, good load balancing in the network, because good bandwidth without good network efficiency is just going to be self-defeating. So I'd say it's interesting when Tomahawk 5 was first introduced, ChatGPT had not yet come onto the scene. And there was some interest in it, for building out general data center infrastructure. But once Gen AI became important, you saw that people had to build out those clusters, as soon as possible. So what we're seeing right now is Tomahawk 6 is the demand is tremendous. The people are saying, I've got to deploy this as quickly as possible to have, the largest XPU clusters, to have the most efficient infrastructure.
I remember 2 years ago when you guys started showing the world kind of the peek behind the curtain, Broadcom. You start to see things like the custom packaging options, you see the CPU, and you got all these now the layers of tiered things. It was the beginning of what was clear that was coming was clustered systems. But the questions came back to, what's the performance? So what I like about the Tomahawk 6, and I would like you to explain, if you don't mind, the performance level, 102 terabits per second. That's kind of industry, scope that at magnitude. Compare what that is. Obviously the scale up's a big story too, but the performance is pretty much the top story. Scope that kind of value. Paint the picture for us. What does that mean?
Yeah, I think, so the two cases I'll bring out are, one for scale up. So, scale up is where you have a very tightly clustered group of GPUs. I mean, it used to be that scale up was, a couple of GPUs connected together, moving to 4, moving to 8. What you see now is that folks want to have, tens of GPUs. And in the future, you want to see hundreds. So with one Tomahawk 6, you can now connect 512 XPUs in a single hop in a scale-up network. And that scale-up network, you'll see that that provides very significant gains as far as performance versus having a distributed scale-out network, because you have much higher bandwidth, much lower latency communication between the GPUs. On the scale-out side, what we're seeing is that you want to reduce the number of networking tiers, you want to reduce the amount of optics, you want to reduce the power in the network, so that way you can put more power into the assets that are making you money, those GPUs. So one example we bring out is for the next generation of GPU clusters, what you'll see is that folks are targeting on the order of 100,000 XPUs, later going to 1 million. With Tomahawk 6, we can connect all of those XPUs in 2 tiers. With a competing technology, you need to have 3 tiers. So that might not seem like a big difference, but what you'll see is that the number of switches for a 3-tier network is more than 3 times the number of switches you'd have for a 2-tier network. Also, the number of optics increases by almost 2/3. And so if you look at the power consumption for those networks, what you'll see today is about 70% of the power goes into the optics. So the total power consumption winds up being almost 2x for a 3-tier network as compared to a 2-tier. And then going along with that, you also, with a 2-tier network, you have lower latency, because now you have 3 switch hops instead of 5 switch hops. And it also makes congestion control much more simple. So you wind up having a much more efficient network. So that demand for the bandwidth is both because on the scale up side, you want to have more XPUs connected together in a single hop. On the scale out side, you want to have as efficient network infrastructure as possible.
I mean, I just love how the scale up and scale out are playing well together, because then you want to have that flexibility. The 512 is a great number, but also there's kind of like scaling laws emerging. I'm paraphrasing, but in AI scaling parlance, can you just share some of the considerations, the requirements? What are some of the factors people are dealing with, and how does that translate to numbers? Because 3 tiers, more points, more failure opportunities, more inefficiencies.
Yeah.
I get that. Scale out's great, scale up's good. But when you start getting into some of the AI scaling math, people who are building the systems, what is the key criteria? What are some of the requirements when they think about that? And what does it deliver? I mean, okay, what does it calculate into? Take us through some of the configuration value.
Yeah, so I think what people are trying to do is, they've seen that as you go to these larger and larger LLMs, that you wind up getting increasing efficiencies. Both the results from those LLMs get better, and also both the amount of CPU time that you need to train those, the end result that you can get by putting more cycles into it winds up getting better. So there is this demand to have as large of a possible network as or a number of GPUs as possible. So what's happening today is that these clusters are starting to get power limited. So what happens often is that you can't even have the whole LLM training built within one building. So you both need to be very efficient as far as the power of the network, so you can put more XPUs within the building, and that way you can have that locality of data transfer within the building, and then also have efficient data transfers across different buildings. So I think the end goal is that you first want to increase the size of the scale up. So what we see is that today it's on the order of like tens of GPUs. People want to go to 512, in the future maybe 1,000 GPUs connected and scale up, and that's going to provide you the most efficiency as far as that training for a language model that can fit within that cluster. And then in the future, just scaling out from that, you do want to see that you can scale to that 100,000 million XPUs efficiently, and for that you need to be able to have as minimal networking equipment as possible, and then also have something where you can minimize the power so you can pack more XPUs within one data center.
The million number, when that was first kicked around, people were like, oh yeah, someday. But it's in the calculation that you guys are looking at with Tomahawk 6. You guys support the clusters. Are people looking at the design from that perspective? Is it how many GPUs you can hang off? And is this where the switch comes in? So is this the value of Tomahawk 6? Obviously, the Ethernet component is obviously a different discussion, but clearly that's the open ecosystem. But like the switch enables more GPUs, more XPUs per hop on the scale up. And take me through where the fit is. Yeah. Where's the value?
So it's going to be more XPUs that are connected with a fewer number of hops, and winds up being much more efficient. There's some data that's been, that's got, published by Meta a few years ago, where they show that in some cases when they're training their language models, they could be waiting over half of the time for the network. So those GPUs are sitting idle during that period of time. So that's, I think, the main goal is to make sure the network gets out of the way, so that way you can have, the most efficient data transfers and let the GPUs do their, the calculations, transfer the data as quickly as possible. The other thing that we're trying to do with Tomahawk 6 is we're trying to make it such that you have the same technology for both the scale up and the scale out interfaces, for a couple of reasons. One is that for these very large clusters, that even though they are being built out to say 100,000 or 1 million GPUs, a lot of the workloads, like if you have a GPU cloud, you'll find that some of those workloads will not necessarily need to use all those million GPUs. So you'd like to have these fungible groups where you can say, for this particular workload for this customer, I want to have this many XPUs that are within a scale-up domain, and then define what the scale-out domain is. So if you use Ethernet both for the scale-up and the scale-out, you have that fungibility. So I think that's one thing that...
Talk about the fungibility. The two things that are jumping out at me with this. One was the fungibility piece of the Ethernet. That's the value. Specifically can be quantified. And there are use cases where if you don't have that, the alternative, you're kind of stuck. And then there's the flapping there's the efficiencies of the hops. Those are two things that actually directly relate to some numbers. You could look at GPU time, power required. So if you're constantly have the problem there with the connections. Those are 2 points. Can you just expand on those? Because I think the fungibility is one big thing. What's your alternative if you're not Ethernet? That's the problem. And then obviously the 3 tiers obviously creates inefficiencies on the GPUs as well as other things. Explain that further.
Well, I think fungibility, I think a step back first, take a look at, the different networking technologies that are being promoted within the data center that, it's pretty much everyone for a long time has said, yes, it's going to be Ethernet for the front end or general data center network. There was a debate in the past about the scale out or the back end, is that going to be InfiniBand or Ethernet? And that's pretty much done. Everyone's saying that's Ethernet now. And now the third domain is what you have for the scale up. So in the past, what people would say is that you need to have, a certain set of operational tools, a certain technology stack for your front end, which is different than your back end, which is different than scale up. So, now fortunately the industry has gone towards Ethernet for scale up and for scale out and for the front end. And the next step is to move it into scale up. So as far as fungibility, it's just going to be as far as operational efficiency within the data center. And the fact, again, that if you have a GPU cloud, you want to be able to say for different workloads that, this is something I'm going to dedicate to this customer, I'm going to dedicate this for a certain workload, and then these interfaces here, I'm going to purpose those as scale up and these as scale out. So there's a lot of efficiency.
So versatility, efficiency.
Exactly.
All right, show some of the products because you got the optic piece here and you got the size of the chips. Let's look at the chips here for a second. Mind if I grab this one?
Yeah, sure, go for it.
This is the big one.
Yeah, that's the really impressive one. This is Tomahawk 6 100 gig.
Okay.
So, one thing we emphasize is that, we've been first to market every generation for a certain bandwidth node. And it's not only that, we've provided the most innovation, the most options for I/O. So with Tomahawk 4, this one had an option for 50 gig SerDes, for 100 gig SerDes, and for co-packaged optics. So even back in Tomahawk 4, we had an option for CPO. Tomahawk 5, we wound up having, a version with 100 gig SerDes and also 100 gig optics, CPO. So Tomahawk 6, this is fairly groundbreaking. I mean, this chip here has,
hold up.
Yeah, so this has 1,024 100 gig PAM4 SerDes. So, I think the industry definitely expected that a 102 chip would come out with 200 gig SerDes, so 512 200 gig SerDes.
And that's speed. That's blazing speed.
That's blazing
that translates to blazing speed.
Yeah, that's kind of, top of the line right now. That's the fastest interfaces you'll find out. I mean, people are looking into 448 gig, but that's probably not going to be for another few years.
It's like, when you go to a car show, it's like this new engine, everyone loves the fastest. So this is, I'm enamored by packaging. I love the innovation around packaging. This chip here, explain this one, what this is doing.
Yeah, so starting off with Tomahawk 5, in that generation of technology, what we did with our SerDes is we made it flexible such that it can drive DAC, it can provide chip to module for standard pluggables, and also directly drive co-packaged optics. So it's the exact same piece of silicon, towards the center, and then it's just, how do we package it? Do we package it with optics or do we have that with electrical I/O? So what's in this chip is, the center silicon is Tomahawk 5. Again, exact same silicon, no software changes needed. And then under this ring, we have all the optics needed for 51.2 terabits per second of networking. Aside from the laser source, which we keep external for field serviceability. Now, to give you an idea of the efficiencies of that, so this is an 800 gig optical module.
You can hold it up higher, yeah.
So this is an 800 gig optical module. So the optics in this Tomahawk 5 with CPO would replace 64 of these. So it's huge efficiencies as far as integration. Gives you a big benefit as far as cost, as far as power.
I mean, just number of connections. I mean, I think you guys have always been driving the interconnect, collapsing the number of components on interconnect and cost. Because you got this cost curve here, right? There's cost and potential reliability. I mean,
I'd say its cost is, it's CapEx and also OpEx. And it's dramatically lower power. An 800 gig optical module today might be on the order of 15 watts. An 800 gig equivalent, that CPO, is on the order of 5 watts. And again, since most of your power, more than half of your power these days goes into optics in the network, it's a huge network-wide power savings.
Talk about...
I think just one interesting point too is with the CPO, is that we're currently measuring data, and what we're seeing in the field is that you actually wind up with higher reliability, fewer link flaps than you do with these discrete optics. And the reason is that you have that optics is sitting right on chip. You don't have intermediate components. So overall, you wind up having a more stable optical link. And it winds up, you find that some of these large data center networks, especially if you've got hundreds of thousands of optics, they suffer a lot of inefficiencies by these link flaps where a link will go down. This, the network transfer.
Okay, so that's where link flapping comes in, here on the connections. And what does that do to the GPU? Same thing? It's just kind of kind of has them recalculate? Does that cause, what kind of problems does that cause?
Yeah, so depending on the severity of the link flap, what can happen is might mean that you need to restart your GPU job. You might need to go back to a previous checkpoint. So it's a lot of wasted GPU cycles. Yeah. And there's some network operators where this is top of mind. This is the major issue they're having in the network. So I'd say as far as reducing those link flaps, what we're doing is, first, I think we want to maximize the use of copper. So within the rack, maybe between racks, depending on the speed of the SerDes, if you can use copper, it's the most reliable, lowest latency interconnect. So our SerDes by far have the longest reach for passive copper. Next step is to have optics that are going to wind up being more stable. And the end goal there, I think the ultimate as far as reducing link flaps, getting the highest reliability is going to be co-packaged optics.
Yeah, co-packaged. So I got these two chips here. Again, one's bigger than the other. The 100's here, and this is the 200 Tomahawk 6. The packaging, and you mentioned copper, versatility is a big thing, so design. So talk about why these chips are different. There's different SerDes levels, but there's reasons why they're bigger.
Yeah.
I always find bigger is better, but it's actually, this is the this is the better chip. Is it the better chip? Well, they're not the same chip.
It depends on the XPU.
I don't know which one's better. Smaller seems better on one hand, but then big is big, right? The big chip. So like, why is the size different? Talk about what that does, because it has to do with some of these cabling and the flexibility reasons. This important point.
Yeah, it's really the speed of the SerDes. It's so the existing ecosystem today for the optics, many of the GPUs, many of the XPUs use 100 gig PAM4. So in that case, you'd like to have the native speed for the SerDes on the switch chip match the native speed for the optics, match the native speed for the XPU. One benefit you'll get for 100 gig PAM4 is also the reach for passive copper is longer. So you can wind up with a bigger cluster based on that. You won't have the density of 200 gig. Yeah. So 200 gig, what you're going to get there is, you can see the package is significantly smaller. I mean, the size of the two chips.
So you move the trade-off optimization to the owner or the cluster, giving them the optionality based on what the size of the cluster is. So in copper, in this case, is distance. What does that mean? Like across the data center, rack, what's the distance we're talking about here?
So for copper in general, for 100 gig PAM4, what we've seen is that from switch to switch, we can get about 4 meters of passive copper, which is about twice the IEEE spec. Going from a NIC to a switch, because the NIC losses are a little bit lower, we can get about 5 meters of passive copper. Moving to 200 gig, depending on the system design, you can get about 2 meters total of copper, passive copper. So generally where you'd see for 200 gig where passive copper will be used is within a rack. So we do see a huge amount of demand for Tomahawk 6, especially with 200 gig SerDes for these GPU racks. Whereas the previous generation for Tomahawk 5, most of the deployments tended to be pizza boxes. And of course, there were some chassis, some blade systems. But what we're seeing is that moving towards these very dense GPU systems, which what they're trying to do is whatever possible to maximize the use of passive copper. And that basically means you have these, these 100 kilowatt plus, racks where they pack as many GPUs, as many switches into it. So that way you can use just passive copper to connect them.
I want to point out that a lot of people look at magic of AI, but in your business, it's not magic. There's years of innovation involved. Trident, Tomahawk, Tomahawk 2, Tomahawk 5 and 6. Load balancing is a big thing. You got global load balancing that's going to enable cognitive routing knowledge. So you're getting smarter in the chips itself. Yeah. The old adage, what's AI for chips and chips for AI? So like getting into what that value is, talk about the global load balancing and that evolution from Trident to Tomahawk 6. What's the lessons learned? What's the advances in the breakthroughs in the technology? And what do you guys have as that leverage and that trajectory of experience? What does that bring to the table?
Yeah. And I think your point about like having experience in these real world deployments of these super large networks is really critical. So with Trident, we had kind of standard ECMP load balancing. With the first Tomahawk, we had some advanced ECMP where we had very flexible hashing. We could introduce a lot more entropy. We could wind up with much better distribution. With Tomahawk 2, we introduced what's known as dynamic load balancing. So whereas before with ECMP and advanced ECMP, you had static load balancing. So you take a look at the packet, you say, here are the fields in the packet, you do a hash on it, figure out where the packet goes. What dynamic load balancing does is it'll look at the link quality and then determine on a packet-by-packet basis which link should this packet go out on. Global load balancing is something that was introduced in Tomahawk 5, and it's gotten a lot of attention. What it does is it takes a look at, it actually gets congestion information from downstream in the network. So what we see, how people use that is they can get a congestion signal from downstream, feed it to an upstream switch, and then the upstream switch knows which link to output the traffic. We take a look. We seem that it's kind of like trying to do like a routing for like Google Maps, where if you're trying to figure out how to get from point A to
it's
B,
15 minutes this way with traffic, and you go this way, kind of thing.
And if it's just if it's something where you're taking a look at the next intersection to find out where the traffic is, and bake in your you take a left turn, right turn, or go straight based on that, you don't know if there's going to be congestion downstream and how to avoid that. So that's really the idea behind global load balancing, is that it has this global intelligence to have the best global path through the network. And then with
on both scale up and scale out across the systems?
So I think GLB will be more applicable to scale out, because with the scale up, it's going to be a single hop. So normally just with the telemetry you'd have from a single switch, you can wind up figuring out what are the loading on the path, how you do the congestion control between the XPUs. So I think it's more where you have these multi-hop, larger networks. So what we've seen actually.
In your tier 2, you have a lot of connections too, so that's going to give you more options.
Yeah, exactly. Yeah, because if you take a look at a closed network, once you get up to the top, the root of the network, there is, by definition of how a closed network is formed, there's only one path to a destination. So once you get up to that point, that root of the tree, at that point you only have one choice. If there's a congested network or a congested path, you have to take that. So you really want to know beforehand which one of those spine switches you go to in order to minimize the path delay, minimize the congestion.
Yeah, that's awesome.
Yeah, and with this global load balancing, I mean, what we've seen is that customers have used it for, really two different ways. One is they'll detect, downstream congestion, find out what the global path is, that's global path. Also to react to path failures. You look at these, 100,000 million XPU clusters, you've got, hundreds of thousands or millions of links, and those links fail. You could have either link flaps or it could just be a complete failure. So what you can do with GLB is that the downstream switch can say, hey, my link has failed. It'll send it to an upstream switch. And now you can know to steer around that, use another set of links. And if you use traditional path steering or link failure detection and mitigation within standard Ethernet networks, it could take about a second to 3 seconds to react to that. Depending on the size of the network, with GLB, it's going to be somewhere in the order of 50 to 100 microseconds. So we're talking about a factor literally of 10,000 times faster.
Yeah, I mean, you look at some of the charts of the scale out, some of the designs of these big clusters. It's a very big, complicated system with a lot of connections, a lot of points with switching. That's needed for this intelligence, because you have a lot of things talking to each other in these new AI scale models. That's a big part of the switch value, right? Am I getting that right?
Yeah, no, absolutely. I mean, just having that global intelligence, first just having the fact that, DLB, our competitors are kind of catching up, they understand the value of that, but adding in that global intelligence provides, much more intelligent decisions that, you wind up having much better load balancing, easier congestion control, and the GPUs, again, just waiting less time to, transfer the data between.
It's an exciting time, Pete. There's a systems revolution going on. You're seeing a lot of value, there's huge demand. Just give us a taste of the demand. I mean, phones ring up, and phones don't really ring off the hook anymore, but literally the demand. Talk about some of the demand that you guys are seeing. Are there use cases that are jumping out with this? Obviously your customer base is probably going to love this, breakthrough performance, flexibility. What's some of the demand appetite like? Can you give us context?
Yeah, I can't talk about numbers, but it's just, I mean, the demand is insane. What we're seeing right now is that, pretty much, as mentioned before, so Tomahawk 5, when that came out, it's like, okay, 51.2 T of bandwidth. We want to upgrade our data center and infrastructure. We'll get around to it at some point. AI hits, and everyone's got to have it as soon as possible. Tomahawk 6 has been that everyone is beating on our door saying, the systems are designed. They're waiting for, for the chip to get into production so they can deploy their networks. And I think what we're seeing right now is that. It's not only the demand is high, but we're also seeing a variety of different systems that are being designed. So of course, the ODMs, OEMs are going to have traditional pizza box-based systems, but we are also seeing a lot of cases where customers want to use Tomahawk 6 both for scale up and scale out, and they have these very custom rack designs. So that's one thing I think that's kind of unique at this point in time, is that before the 102T, I think the current generation of XPU racks, people were reluctant to go to, liquid cooling. They were reluctant to have, kind of custom rack designs. We don't need to have liquid cooling for Tomahawk 6. A lot of the systems are going to be air-cooled. But what we're seeing is that, they're designing these completely custom racks, completely fully engineered racks, just to be able to leverage Tomahawk 6, to leverage that 200 gig SerDes density, and have something that's going to provide, the lowest latency, the most reliable interconnect for those XPUs in the rack.
Yeah, I think that's a great point. I think the interconnect innovation also gives that design option where you don't have to over-rotate on liquid cooling and power envelopes that they're struggling with.
Yeah.
All right, final question because I have to ask, what's the vibe inside of Broadcom? Because, when the new chip gets shipped into the team, they start testing it. Is it going to work? I mean, what was it like? What's it like inside? I mean, this is a pretty big announcement that hits all the boxes on numbers. You got packaging, reliability, kind of hits all the sweet spots. Again, the speeds and feeds are off the charts. What's it like internally? Are the engineers loving this?
Oh, I mean, they're totally loving it. Part of it too is that, because I started off, I was doing like chip design and processors a long time ago, and I mean, just the fact that, they see the demand, they see the applications for this. I mean, it's really exciting for the engineering team. And we're way ahead of the competition as far as delivering this. As far as features, I mean, we've never seen anything in our previous generations where competitors have had better features, better load balancing, et cetera. So there's a tremendous amount of excitement. We really beat on the team to get this chip out because it's an incredibly complex device. But yeah, I mean, the mood is very, very positive.
It's like that engine, when you get something that's that good. It's funny, in the industry, we always have these waves of innovation in the innovation cycles. It is about speeds and feeds, and then it moves to solutions. This enables those solutions. This is the AI scale we're seeing. It's kind of new scaling laws coming out. Thanks for coming on. Appreciate it, the deep dive.
Yeah, thank you very much. It was great being here.
Pete Vecchio, Data Center Switching Product Line Manager at Broadcom, bringing the Tomahawk 6 innovation across the board, interconnects, you got the global load balancing, a lot of intelligence, enabling the AI solutions that are going to be coming on the market very, very fast. I'm John Furrier with theCUBE. Thanks for watching.